Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the logistics tracking system, the system that powers real-time shipment, fleet, and ETA visibility for modern supply chains. We'll cover how platforms track millions of vehicles and packages, compute live ETAs, handle missed scans, and alert dispatchers and customers when exceptions happen. Whether you're preparing for a senior engineering interview or building logistics infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the logistics tracking system, the backbone of modern supply chains that tells shippers, carriers, and customers exactly where a package or vehicle is, when it will arrive, and what exceptions need attention. If you have ever ordered something online and watched the package move from warehouse to truck to doorstep, or wondered how fleet managers coordinate thousands of vehicles across cities and countries, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building logistics infrastructure, let's get into it. Here is the core problem. A retail company ships millions of parcels every day through a network of warehouses, sorting hubs, line haul trucks, last-mile vans, and delivery partners. Customers expect real-time tracking and accurate estimated times of arrival. Dispatchers need to know which trucks are running late, which drivers are idle, and which routes need rerouting. Operations teams need scan compliance at every checkpoint. But behind the scenes, the data is fragmented. GPS devices drop offline inside tunnels, scanners miss a hub check-in, drivers take unplanned detours, and ETAs drift because traffic or weather was not modeled. A single missed scan can make a package look lost. A stale GPS point can make a truck look idle, and a bad ETA can erode customer trust. The business needs a centralized logistics tracking system that ingests location events, scan events, and telemetry at scale, computes live ETAs, alerts on exceptions, and gives every stakeholder a single source of truth. Let's walk through the functional requirements. First, the system must ingest high-frequency telemetry from many sources: GPS trackers on vehicles, mobile driver apps, handheld barcode scanners, warehouse management systems, shipping label APIs, and partner carrier feeds. Second, it must track the shipment lifecycle end-to-end, from order creation, pickup, hub arrivals and departures, outbound line haul, last-mile assignment, attempted delivery, and final proof of delivery. Third, it must compute estimated times of arrival that are continuously updated based on live location, route, traffic, and historical performance. Fourth, it must provide fleet visibility: vehicle positions, driver status, fuel or battery levels, utilization, and route adherence. Fifth, it must support exception handling and alerts for missed scans, delayed departures, geofence violations, route deviations, and failed delivery attempts, with notifications to dispatchers, customers, and merchants. These 5 capabilities make the system operationally useful. Now the non-functional requirements. The system must be near real-time. A vehicle location update should be visible to dispatchers within seconds, not minutes. It must handle massive scale because a large logistics network can have hundreds of thousands of vehicles and millions of shipments, emitting events every second. The system must be geographically distributed, with data centers or edge nodes close to major logistics hubs to reduce latency and comply with data residency. Accuracy matters. Stale GPS coordinates, duplicate scan events, and clock skew must be handled correctly. Availability is critical because tracking and fleet operations run 24/7. The system must be resilient to network partitions, especially when vehicles move through areas with poor connectivity. Security and privacy are essential because location data is sensitive and shipment data may contain personal information. And the system must be cost-efficient at scale because storing every GPS point forever is prohibitively expensive. Here is the high-level system architecture. On the left, data producers include GPS trackers, driver mobile apps, barcode scanners, warehouse systems, carrier partner APIs, and customer order systems. These events flow through a load balancer and API gateway into a Kafka ingestion layer, where different topics handle location events, scan events, telemetry events, and partner updates. A stream processor consumes the location topic, validates events, deduplicates them, and updates a hot geospatial store that powers live maps and ETAs. A separate scan processing pipeline updates the shipment lifecycle state in a transactional database. The ETA service runs a continuously updated model that combines live location, planned route, and traffic data. The fleet service tracks vehicle and driver assignments. The notification service watches for state transitions and exceptions, then sends alerts through push, SMS, or email. The dashboard and mobile APIs serve customers, drivers, and dispatchers. The analytics backend stores aggregated historical data for reporting and optimization. The key metrics to memorize: cold on-time delivery percentage, the fraction of shipments delivered within the promised window. ETA accuracy, often measured as the percentage of deliveries that arrive within a defined tolerance of the predicted time. Tracking event latency, the time from a GPS fix or scan to it appearing on the map. Scan compliance rate, the percentage of required checkpoints that are correctly recorded. Fleet utilization, the ratio of active vehicle time to total available time. First attempt delivery success rate, the fraction of deliveries that succeed on the first try. Geofence adherence, the percentage of vehicles that stay within planned routes or zones. And exception resolution time, how long it takes operations to detect and resolve a delivery issue. These metrics are what logistics leaders actually care about. Let's trace the end-to-end user journey. A merchant creates a shipment in the logistics platform and prints a barcode label. A driver scans the package at pickup, and the customer immediately sees the status change to picked up. The package travels through a regional hub, where an automated scanner records arrival and departure. It is loaded onto a line haul truck whose GPS tracker streams location every 10 seconds. The ETA service predicts arrival at the destination hub based on live traffic and historical line haul times. After sorting, the package is assigned to a last-mile van. The driver follows an optimized route, scanning each package before delivery. The customer receives a push notification when the driver is 10 minutes away, and another when the package is delivered with a photo proof. Meanwhile, a dispatcher monitors the fleet dashboard, spots a van that deviated from route, and reroutes another driver to cover the missed stops. Every stakeholder has visibility, and the system surfaces exceptions before they become complaints. The core models and algorithms. The shipment lifecycle is a state machine that moves through created, picked up, in transit, arrived at hub, out for delivery, attempted, delivered, and exception states. The event stream model treats every scan, GPS fix, and telemetry update as an immutable event with a timestamp, source identifier, and geohash. Geospatial indexing partitions the world into grid cells, so that queries like find all vehicles near this warehouse are fast. The ETA engine combines map routing, live traffic, historical segment durations, and current vehicle position to predict arrival windows, usually recalculating on every significant location update. Route optimization uses vehicle capacity, time windows, driver shifts, and delivery priorities to build efficient last-mile plans. Exception detection applies rules and anomaly detection to flag missed scans, stalled vehicles, geofence breaches, and late departures. The key trade-off is precision versus cost. More frequent GPS updates give better tracking but increase ingestion and storage costs dramatically. Now the low-level design deep dive. The ingestion layer accepts events from devices over MQTT or HTTPS and writes them to Kafka topics partitioned by vehicle or shipment identifier. A location stream processor validates coordinates, deduplicates using a device sequence number, and writes the latest position to a hot geospatial store such as Redis with geospatial indexes or a Cassandra cluster partitioned by geohash. The shipment state service maintains a transactional record in a relational database or a strongly consistent document store, applying scan events to advance the lifecycle state machine. The ETA service maintains a routing graph cache, subscribes to relevant location updates, and recomputes ETA whenever a vehicle crosses a route segment boundary. The notification service reads state transitions and exception rules, then sends templated alerts through push, SMS, or email providers. For resilience, the system buffers events on the device when connectivity is poor and replays them with correct timestamps upon reconnection. For analytics, hot location data is downsampled and archived into a columnar store for trend analysis and optimization. Key takeaways for your interview. First, a logistics tracking system is an event-driven, geospatial, and state machine problem, so emphasize ingestion pipelines, geospatial indexing, and lifecycle tracking. Second, always separate hot path concerns like live vehicle positions and ETAs from cold path concerns like billing, audit, and analytics because the latency and storage requirements are very different. Third, ETA accuracy is a modeling and data freshness problem, so discuss how you combine routing, traffic, historical data, and recalculation triggers. Fourth, the hardest design challenge is handling scale and cost while keeping tracking fresh, so mention downsampling, delta updates, and edge buffering. Fifth, operational reliability matters because the system is used by dispatchers and customers in real time, so talk about resilience, geofencing, exception detection, and multi-region deployment. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the logistics tracking system. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the logistics tracking system. We covered the full picture, from telemetry ingestion and Kafka pipelines, through geospatial indexes, shipment state machines, ETA engines, and the low-level design of the event pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.